class. In today's lecture, we proceed to chapter number 3, which discusses about algorithms. We start with this topic, integers and division. Okay, so we start with divisibility. Suppose we have two positive integers denoted as n and d, where the integer n is greater than d and the integer d not equal to 0. When we divide n by d, so we have the following equation number 1. All right, so it means we divide n by d, so we obtain it is equal to q plus r over d. Okay, where q and r are both integers, and for the integer r, okay, it is located in the range between 0 and d. It can be greater than or equal to 0, and it is smaller than d. When it is not equal to 0, so it must smaller than d. And the value for the r over d, so the value is between, it could be greater than or equal to 0, and if it is not equal to 0, so it is less than 1. Okay, so that means the value for the r over d is, if r not equal to 0, so the value for the r over d is 0 point something. Okay, it's between 0 and 1. Alright, so we call n is dividend, d as divisor, q as quotient, and the integer r as remainder. Alright, so the integer n is called dividend, d is what we call as divisor, okay, d is the divisor, q is the quotient, this one is the quotient, while the r is the remainder, okay, remainder. Alright, so we consider the following two cases for division operation. So when the value for the r equal to 0, that means there is no remainder, the r equal to 0. So we have the equation number 1 becomes n over d equal to q, where q is an integer. Alright, that means when we divide n by d and the outcome is an integer, so that integer is the quotient value of that division. Okay, so for this kind of case, we can say that n is divisible by d. Okay, n is divisible by d because when we divide n by d, there is no remainder. Okay, in other words, we also can say d divides n. Okay, when we are referring to d, so we say that d divides n, and it is denoted by horizontal line between d and n. Okay, so if we have this kind of notation, that means d divides n. When we divide n by d, so there is no remainder. The outcome is an integer q, which is the quotient. Okay, if the value for the remainder not equal to 0, that means we have the complete equation number 1. Okay, so we have n over d equal to q plus r over d, and this value is a non-integer value. Okay, it's non-integer value. So if we have this kind of situation when we divide n by d, the outcome is a non-integer value. So what does it mean? That means n does not divisible by d, because when we divide n by d, so we have a remainder not equal to 0. Okay, the remainder not equal to 0. Okay, in other words, we also can say that d does not divides n. Okay, so instead of we put d and n between horizontal line, we do like this to indicate this is the negation. That means d does not divide n. Okay, all right, so I give you some example to make it clear. So let's say we have n equal to 12 and we have a d equal to 4. So when we divide n by d, the outcome is an integer q, okay, which is 3. 3 is an integer. So what does it mean? That means the remainder equal to 0. So we can say that 12 is divisible by 4. And we can also say that 4 divides 12. Alright, we move to the next example. We have 100 divided by 25. Again, the outcome is an integer 4. So the integer 4 is the quotient without any remainder. So what does it mean? That means when the remainder equal to 0, the number 100 is divisible by 25, and also we can say that 25 divides 100. Okay, so how about the third one? Again, we obtain this one. The outcome is an integer. So 30 divided by 10, the answer is 3. So 3 is an integer. There is no remainder. So again, we say that 30 is divisible by 10 or 10 divides 30. Okay. Alright, so we have the following another 3 cases. So in these 3 cases, we have 15 divided by 4. The outcome is 3 point something, right? Okay, it is non-integer value. Okay, 3 point something. So it is a floating point value. So what does it mean? Since the outcome is a non-integer, so that means the remainder not equal to 0. Okay, but it must less than d. Our d is equal to 4. Okay, once it is not equal to 0, so it must less than the divisor d. Okay, so since the remainder are not equal to 0, so we can say that 15 does not divisible by 4, and also 4 does not divide 15. Okay, so we have this kind of notation to know, which is the negation of divides. Okay, so same goes with the next case, 101 divided by 25. The outcome is again is non-integer value. We got 4 point something. Okay, 4 point something. So the 4 is the quotient, and the floating point, after we remove the quotient, it becomes 0 point something. The 0 point something is actually r over d. Okay, so the value is greater than 0 but less than 1. Okay, this value. All right, if you remove the quotient, so the remaining value is 0 point something, so that value is r over d. All right, so the value is greater than 0 but less than 1. Since the remainder not equal to 0, so we can say that 101 does not divisible by 25, and so we can say that 25 does not divide 101. Okay, and the next example, again we obtain a non-integer value when we divide 31 by 10, so the answer is 3.1. Okay, so 3 is the quotient, so when we remove the 3, so the remaining value is 0.1. So that value is the value for the r over d. Okay, r over, this one is r over d. So r over d lies between, it is greater than 0 but less than 1. Okay, since the outcome is a non-integer value, 31 divided by 10 but divided by 10 is a non-integer value. So we can say that 31 does not divisible by 10, and 10 does not divide 31. Okay, 10 does not divide 31. Okay, so we consider the following theorem. Let's say we have 3 integers m, n, and d. Okay, if the integer d divides m, and the integer m divides another integer which is n, so we can say that the integer d divides the integer n. Okay, so if d divides m and d also divides n, okay, so that means d divides m plus n. Okay, not only plus, it is also divides m minus n. Okay, it is applicable to both operations, addition and subtraction. Alright, so when d divides m and d divides n, so d divides either m plus n and also m minus n. Okay, and the fourth theorem, if d divides m, then d divides m multiply with any number. Okay, let's say we multiply with n. Okay, it is still divisible by d. Okay, we consider the following corollary. If d, m, and n are integers where d not equal to 0, such that d divides m and d divides n. Okay, so d divides the multiple of both m and n. Okay, so d divides the addition of the multiple f and n, m and n, so d divides mp plus nq. Okay, where both p and q can be any integer. So this one is the multiple of m, and this one is the multiple of n. So when we add together these two values, so the addition is still divisible by the integer d. Okay, now we reconsider the equation number 1. This is the equation number 1 that we considered in the earlier slide. Okay, so we have n over d. When we divide n by d, the outcome is equal to q plus r over d, where r can be equal to 0, or r also can be greater than 0 but less than d. Okay, so from the equation number 1, we can rearrange this equation. We take d to the other side, we take d to the right hand side. So what happened to the equation? So it becomes n equal to dq plus r. Okay, when we take d to the other side, to the right hand side, so we obtain the equation number 4. Okay, from equation 1, now it becomes equation number 4. Okay, so according to the division algorithm, let's say we have two positive integers n and d when n is greater than or equal to d. Okay, so they are unique. Okay, so the value for the quotient and remainder is unique for every n and d. Okay, so for every n and d, the value for the quotient and remainder are unique. So this is based on the division algorithm. Okay, so with the value for the r lies between the range, it could be equal to 0, but if it is not equal to 0, so it must be greater than 0 but less than d. Okay, such that all these numbers satisfy this equation. Okay, n equal to dq plus r. Okay, so the following notations are used to express the quotient q and the remainder r. So basically in programming, we can use the following operations, div and mod. Okay, so for a div d, so the outcome is an integer q, where q is the quotient. Okay, so when we write a mod d, okay, so this operation actually looking for the remainder r. Okay, so the outcome is the remainder when we divide a by d. Okay. Okay, now we consider the following two definitions regarding the floor and also ceiling. Okay, for the floor of x, it is denoted like this. So we have this kind of parenthesis for floor. Okay, this kind of parenthesis. Okay, for floor, and this kind of parenthesis denotes the seal. Okay, the ceiling. Okay, as you can see here, this is the following other differences. Okay, between these two parentheses. Okay, for the floor of x, it is denoted like this. So the floor of x is the nearest integer but less than or equal to x. Okay, for example, the floor of 8.33 is the integer 8 because the integer 8 is less than 8.33. Okay, it is less than it is the nearest integer that is less than 8.33. Okay, so how about the floor of negative 8.5? Okay, in the real number line, so this is 0, so we have negative 8 and negative 9. Okay, so the floor for the negative 8.5 is the nearest integer less than or equal to negative 8.5. Okay, so negative 8.5 is located here. So obviously, the nearest integer that is less than 8.5 is negative 9. Okay, because the closer the number to the negative infinity, that means the number becomes smaller. Okay, then all the integer the negative numbers closer to 0. Okay, so from that, negative 9 is the nearest integer that less than negative 8.5. That is why the floor of negative 8.5 equal to negative 9. So the floor of integer, it becomes the original number. For example, the floor of negative 7, it is equal to negative 7. Okay, finish with floor. We move to ceiling. The ceiling of x denoted like this kind of parenthesis. So it is the nearest integer that is greater than or equal to x. Okay, greater than or equal to x. For the floor, it is less than. For the ceiling, it is greater than. Okay, I hope you can see clearly the difference. Okay, for the nearest integer greater than or equal to x, so that is the ceiling of x. For example, the ceiling for the 8.33, it is equal to 9 because 9 is the nearest integer that is greater than 8.33. Okay, so for negative 8.5, the nearest integer that is greater than negative 8.5 is equal to negative 8. Okay, not equal to negative 9 because negative 8 is greater than negative 8.5 while negative 9 is less than negative 8.5. Okay. Again, for any integer, the ceiling for that integer is the original integer. Okay, the ceiling for negative 7 it is equal to negative 7. Alright, so from the equation number 1, when we divide n over d equal to q plus r over d. Okay, so let's say the question asks you to find q. Okay, so to find q, we can rearrange this equation number 1 until we obtain q at the left hand side alone. Okay, we rearrange the equation number 1, we put q to the left hand side and we put other than q to the right hand side, so we obtain this equation. So this equation n over d minus r over d actually is the floor. Okay, the floor of n over d. Okay, the floor of n over d, and it is an integer value. Okay, it is the integer value. So how about the r? Okay, if we again rearrange the equation number 1 and our aim is to obtain r, that means we rearrange the equation number 1, we put r to the left hand side and we put everything other than r to the right hand side, so we obtain this equation. Okay, so we have, first of all, we have r over d, okay, at the left hand side equal to n over d minus q, and then we know that q is equal to the floor of n over d, so we replace q with the floor of n over d like this. Okay, so from this equation is r over d, so our aim is to obtain r, so we take d to the right hand side, so we obtain the final equation where d equal to n over d minus the floor of n over d, we multiply by d, so we obtain the value for the remainder. Okay, so I give you the following example. Okay, some questions ask you to find the div, and some questions ask you to do the mod operation. Okay, so for the div operation, that means we are looking for the quotient value, and for the mod operation, that means we are looking for the remainder value. So we start with the first example. So the given number div 44531. So when we divide the value by the dividend by the divisor, so we obtain the value for the q, okay, which is the floor of n over d. So the floor is equal to 39. Okay, whenever you divide an integer n over d where n is greater than d, so whenever you obtain the result is non-integer value, okay, so the integer part before the decimal point actually is the quotient value. Okay, when you press a calculator, you divide 1745341 divide by 44531, the outcome is 39 point something, right? So 39, which is the number before the decimal point, is the value for the quotient. Okay, so that is the value for the quotient. And if we remove the value for the quotient, okay, we remove the value for the quotient, the remaining value is 0 point something, right? So the 0 point something is r over d. So basically the 0 point something after we remove the value for the quotient is r over d, because r over d lies between 0 and 1. Okay, when r equal to 0, so obviously the value equal to 0. But if r is not equal to 0, that means r is greater than 0, but it must r over d is greater than 0, but it must be must less than 1. Okay, that means the value for the r over d is equal to 0 point something. Okay, r over d is lies between 0 and 1. Okay, while the value for the r alone is 0 and it must less than d, the value for the r. Okay, so the quotient of this question is equal to 29 for the second one. Okay, when the value for the n is smaller than the value for the d, the dividend is smaller than the quotient the divisor, so the quotient equal to 0. So when the dividend is negative, no problem, you can still do the same operation as usual, and the integer value, the floor of this division is equal to -3. So -3 is representing the quotient value. Okay, for the fourth question, we have 34311 mod 4366. So this value, okay, this operation is looking for the remainder, so you just simply use this formula, okay, to find the remainder. Okay, so n over d, and then we minus with n over d, but we take the floor value, and this the value inside the parenthesis we multiply with d, so that we obtain the value for the remainder. Okay, this one there is no 9, so only 3774. Okay, so the outcome is 374. Okay, for the next one, again, negative value, no problem. Just insert the value for the dividend and divisor into this formula. So we obtain the value for the R. The value for the R, which is the remainder, equal to 1129. Okay. And for the last one, again, the value for the modulo, but this time the dividend is smaller than the divisor. Okay. So the remainder is equal to the original value of the dividend, 3224. Okay, now we move to the next topic, okay, about modular arithmetic. So let's say we have three integers. We have a, b, and m, where m is greater than or equal to 1. Okay, so if the integer m divides, okay, the subtraction of a and b, okay, means a minus b is divisible by m. When we divide a minus b by m, the outcome is an integer. Okay, the outcome is an integer. A over b we divide by m, the outcome is an integer. So if we have this kind of case, okay, we can say that both a and b are congruent modulo m. Okay, if a minus b is divisible by m, when we divide a minus b by m, the answer is an integer, or the outcome is an integer, then we can say that a and b are congruent modulo m. Congruent modulo m. Okay, so this is the congruent notation. We have triple horizontal line. Remember, the triple horizontal line is totally different with double horizontal line. This one could be representing either more congruent, and also it represents equivalent relation. Okay, while for this notation, it is representing equal sign. Okay, it is an equal sign representing the equal value of left and right hand and side. Okay, for this one, it could be congruent or equivalent relation. Okay, so be careful with the notation. It's totally different between this notation, the triple horizontal line, and this double horizontal line. So for the congruent, we use the triple horizontal line, and we put the modulo value inside parentheses like this. So A congruent B mod M. Okay, so there's a difference between A mod N. That means we are looking for the remainder when we divide A by N. Okay, so we put mod N without any parenthesis. But for the congruent relation, we put the modulus value M inside parenthesis. So A congruent B mod M, we put the mod M inside the parenthesis. So how to read this relation? So we read as A congruent B mod M. Okay, so what happened if A over B, so A minus B will give you a non-integer value. Okay, A minus B divides by M equal to Q plus R over D, which is a non-integer value. So what does it mean? That means A and B are not congruent modulo M. Okay, not congruent because doesn't satisfy the condition to be congruent. A and B do not satisfy the condition to be congruent modulo M, because when we divide a minus b by m, the outcome is a non-integer value. So we say that a and b are not congruent modulo m. Okay, so how to write this mathematical relation? So we write it like this: a not congruent, okay, not congruent, b, we put the modulus value inside parenthesis. So note that m divides a minus b means that a minus b over m equal to q, where q is an integer, while the remainder is equal to 0. Okay. So for example, since 37 minus 2 is 35, and 35 is divisible by 7, because 35 divided 7 equal to 5, 5 is an integer. So we can say that 37 is congruent to modulo 7. Okay, so this is the way how to write this relation. 37 congruent to modulo 7. That means 37 minus 2 is divisible by 7. So how about this one? 37 minus 1 equal to 36. So we divide by 6. The outcome is 7 point something. Okay, which is, that means the value is non-integer value. So we know that the remainder is not equal to 0. So when the remainder not equal to 0, okay, where a minus b, 37 minus 1 do not divisible by 5. So we can say that 37 do not congruent, say 1 modulo 5. Okay, not congruent. Okay, modulo 5, you put the modulus value inside parenthesis. Okay, for the negative value, okay, we have negative values. We have negative 1 and 11. Okay, so we have negative 1 and 11. So negative 1 minus 11. Okay, divide by the modulus m. Okay, the value for the m. So the outcome is an integer, which is negative 1. Negative 1 is an integer. So what does it mean? That means negative 1 congruent 11 modulo 12. As long as both numbers satisfies this condition, okay, I mean the a and b satisfy this condition, a minus b divisible by m, so we can say that a and b are congruent modulo m. Okay, again, we still play around with the equation number 1. Okay, we reconsider the equation number 1. N divides by d. Okay, the outcome is q plus r over d. So from the following equation, if we take d to the other side, to the right hand side, so we obtain the equation number 4. By again rearranging equation number 4, okay, if we take r to the other side, to the left hand side, so we have n minus r equal to dq, and then we take d to the other side, so we have n minus r over d equal to q, where q is an integer. So since n minus r is divisible by d, because n minus r over d equal to an integer value q, so based on the definition of congruent relation, that means d divides n minus r, and this implies that n and r are congruent modulo d. Okay, so the dividend congruent the remainder modulo the divisor. Okay, only if all these three numbers satisfy this condition, then we can say that n congruent r modulo d. Alright. Okay, so now we consider the following theorem. Let's say we have three integers a, b, and m, where the integer m is greater than 0. Then a congruent b mod m, okay, if and only if a mod m equal to b. Means, what does it mean? That means only if and only if a divides by b, the remainder, a divides by m, the remainder is equal to b. Then we can say that a congruent b mod n, mod m. Okay, because this one is the dividend, this one is the remainder, this one is the divisor. Okay, again, so a congruent b mod m if and only if a mod m equal to b. That means when we divide a by m, the remainder is equal to b. Okay, B mod mod M. Okay, so we consider the following example. Note that 37 mod 5, when we divide 37 by 5, okay, so the remainder is equal to 2. Okay, so that means that is the value of the modulo reduction operation. The outcome is 2. When we divide 7 by 5, okay, the remainder also equal to 2. Because of that, so we can say that 37 congruent 7 modulo 5, because it satisfies the following, all these numbers satisfy the following theorem. Okay, 37 mod 5 equal to 2, 7 mod 5 also equal to 2, because these two numbers are equal. So that means 37 congruent 7 modulo 5. Okay, so everything in this example based on the following theorem. Okay, we have another theorem. Let's say we have positive integer m. So if A congruent B mod m and C congruent D mod m. Okay, that means we have two congruences with the similar modulus value. This one is mod m, this one also mod m. Okay, so from this relation, so we have the addition. Okay, A plus C congruent B plus D mod m. So this congruent holds or true. Okay, based on the following relation. Okay, so not only for addition, so it is also applicable to multiplication. So A times C congruent B times D mod m. Okay, so from these two relations, what does it mean? So A plus C minus B plus D is divisible by m. AC minus BD also divisible by m. Okay, that means m divides A plus C minus B plus D, and also m divides AC minus BD, because this come from the definition, because these two relations hold, so that means the following are true as well. Okay, so I'll give you a numerical example. Suppose we have two congruences, 33 mod 3 33 congruent 3 mod 5 and 77 congruent 7 mod 5. Okay, so based from the previous theorem, so we know that 33 plus 77 congruent 3 plus 7 mod 5. So after we compute the operation inside the parenthesis, we have this congruence relation, 110 minus 10 mod 5. Yes, we can verify whether this congruence is true or false. So 110 minus 10 equal to 100. So 100 is divisible by 5. Okay, the outcome is n integer. So this congruence true. So for the multiplication, 33 times 77 congruent 3 times 7 mod 5. So if you want to verify, so we compute this value and this value. So we minus 2541 minus 21. So the value is divisible by 5. Okay, that means this congruence also holds. Okay, we have the following corollary, and this corollary is very useful when we are dealing with large numbers. Okay, so let's say we have three integers a, b, and m, where the integer m is greater than 0. Then a plus b mod m. Okay, let's say a and b are both large integers. Instead of you directly do the modulo operation, means find the remainder when a plus b divide by m. So we can do the modulo reduction step by step. Okay, that means we reduce the value for the m first. We make it smaller. From a, it becomes a mod m. And the b also can be reduced, become b mod m. Okay, so these two numbers are smaller than the original a and b. Okay, so up to we obtain the smaller numbers, so we can perform the addition, and later on we do again the modulo reduction. Okay, we mod by m. That means we find the remainder when the value divided by m. Okay, so It is also applicable for multiplication. So AB mod M, instead of directly multiply the value of A and B, because these two numbers we assume is a large numbers, A is large, B also large. If you multiply, then we obtain larger number. So to do the modulo reduction, sometimes it could be cumbersome. Okay, so instead of we do it directly, we can do it part by part. So you multiply so we do the A mod M first. Okay, so this value is smaller than A, and we also do the operation B mod M. Again, this value also mod less than B. So we have a smaller numbers, A mod M and B mod M. Then we do the multiplication, and then we can reduce mod M. So it becomes easier for us to do the calculation. Okay, so this corollary is very useful when we need to deal with large numbers A and B. Okay, for the next topic, we discuss about arithmetic modulo M. Okay, for the arithmetic modulo M, we define the set of integer mod M. It is denoted like this, Z sub M. That means this, for this kind of notation, that means this is an integer set, a set of integers. Okay, from the negative infinity, okay, till let's say -2, -1, 0, 1, 2, and it goes up to positive infinity. So this is the set of integers. Okay, but when we put subscript M, okay, Z sub M, that means the entries for this set are limited to all integers between 0, that means including 0, until M minus 1. Okay, that is what happened to this set when we put the subscript M. So the entries now become smaller. Okay, the number of entries becomes smaller. So the set starts with 0 as the smallest element, and then it moves to 1, 2, up to M minus 1. Okay, let's say the example, okay, no example. Okay, let's say our M is equal to 7. So the Z7, so it contains entries from 0 as the smallest entry, and then followed by 1, 2, 3, 4, 5, and 6, because 6 is 7 minus 1. So we stop at 7 minus 1. So we have a 6 as the last answer, the last element for this set. Okay, for the Z sub 7. Okay, so we can do operations on this set. Okay, the set of integer modulo M, which is denoted by ZM. So we can do operations on this set defined as follows. Okay, so we have the addition operation. Okay, addition operation denoted again by plus subscript M. So that means this operation is the operation inside the set of integer modulo M. Okay, so that means A plus B. Okay, A plus B, the outcome must be reduced modulo M. Okay, so what does it mean? That means we want to find the remainder when we divide A plus B by M. Okay, we are looking for the remainder value. Okay, so that value is always smaller than belongs to the set of ZM. Okay, for the multiplication, we use the multiplication operations as usual, but then we have addition of notation. We have subscript M to indicate this is an operation inside the set of integer modulo M. Okay, so we multiply A multiply B, we have this subscription, so it is equal to A multiplied by B, and then we reduce modulo M. Okay, that means we're looking for the remainder when we divide A times B by M. Okay, so we are looking for the remainder, and that value belongs to this set. Okay, so R is an integer, belongs to the ZM set. So the both operations, okay, for addition and multiplication modulo M, okay, denoted like this. Okay, these notations are called addition and multiplication modulo M. Okay, because we want the outcome belongs to the set of integer modulo M. Okay, we want the outcome belongs to the set of integer modulo m. When we use these operations, we are said to be doing arithmetic modulo m. So these operations is what we call as the arithmetic modulo m. Okay, I give you a numerical example. So let's say we have 7 and 9. Okay, we do the operation addition modulo 11. And we also have 7 times 9. Again, we do the operation modulo 7. Okay, so to solve this problem, we do the operation as usual, addition and multiplication, but then the outcome must be reduced modulo 11. Okay, must be reduced modulo 11 to ensure that the outcomes 5 and 8 belong to the set of integer modulo 11. Okay, so the set of integer modulo 11 contains the integers between 0 up to 10, because 10 is equal to 11 minus 1. So obviously, both 5 and 8 belong to the set of integer modulo 11. Okay, so the operations plus and minus times modulo m satisfy the following properties. Okay, the four properties. The first property is closure. That means if both numbers a and b comes from the set of integer modulo m, so after we do the operations plus and multiplication modulo m, so the outcome also belongs to the set of integer modulo m. So this is what we call as closure property. Okay, the inputs come from the same set as the output. The output also belongs to the same set as the inputs. Okay. Next is associativity. That means we play around with the parentheses. Okay, let's say we have 3 integers modulo m. Okay, a, b, and c. So if we do the operation inside the parentheses first, a plus modulo m and b. Okay, a plus b mod m. And then we add with this value c and we do the modulo operation. The answer is still same if we do the operation inside this parenthesis first and then we add with a. Okay, left hand side equal to right hand side. Parenthesis means we solve that operation first. Okay, so that means left hand side equal to right hand side. So that's why both operations satisfy the condition for the associative property. So other than closure and associative property, so both operations also are commutative. Also commutative means we change the position. Okay, we change the position. In the left hand side, we have a plus b. So at the right hand side, we change the position between a and b. So it becomes b plus a. Okay, so this value always equal to this value. The outcome still same. Okay, a plus b mod m equal to b plus a mod m. So same goes with multiplication. So a times b it is equal to b times a mod m. So commutative is about we change the position. So the commutative property also holds for the arithmetic modulo m. So other than commutativity, we also have identity elements. So if a and b are integers modulo m, then a plus 0 equal to 0 plus a mod m, it is equal to a. Okay, so that means 0 is an identity element for addition. Okay, because after we do the addition, we obtain the original value. So that means 0 is an identity element for addition modulo m. So for multiplication, if we multiply any number inside the set of integer modulo m, we multiply with 1, so we obtain the original value a. Okay, and then we a times 1 or 1 times a, the outcome still same a. So what does it mean? That means the integer a is an identity element for multiplication modulo m. Okay, so remember the identity element is for addition is 0 and the identity element for multiplication is 1. Okay, so because we have identity, that means we have inverse. Okay, so if a belongs to the set of integer modulo m and the integer a not equal to 0, then a plus m minus a equal to 0. Okay, because we obtained the identity element for addition modulo m, which is 0. That means m minus a is an additive inverse of the integer a modulo m. Okay, again, so because a plus m minus a mod m equal to 0, and 0 is the identity element for addition modulo m. So that means, okay, so what does it mean? That means m minus a, which is added to a. So m minus a is an additive inverse of a modulo m. So we have to write all these terms incomplete, okay, because we have the modulo operation. We cannot simply say that m minus a is an additive inverse of a without the modulo m. Cannot, because we play with the set of modulo m. So we have to say this sentence completely, okay, because m minus a is an additive inverse of a modulo m. Okay, modulo m. Okay, so for distributive, okay, distributive, that means we expand the parenthesis. Okay, so let's say we have three integers from the set of integer modulo m. Then a times b as a times, we do the operation in parentheses first. So it is equal to, we multiply this one, we multiply this one, and then we do the operation of addition. Okay, so it is also applicable to this operation. Okay, distributive. So we have the combination between two operations, addition and also multiplication. So we can expand this operation from a plus b in parentheses times c. So we can multiply c inside the parentheses. Okay, so we obtain a times c mod m plus a b times c modulo m. Okay, this is what we call as distributive property. Okay, so that's the end of this part.